So when we verify the functionality of the D flip-flop, we are looking at how many aspects. What are the aspects we are looking at? For example, if it's a D flip-flop, it's passing D to Q, and if it's rising edge triggered or level triggered, right? And for this application, so let's be clear on the goal of this effort here. So we are trying to find a particle D flip-flop that we can use for our ADC, right? So if you look at the registers, let me open the circuit, see if we can find the circuits. I think I may have it here. If not, then we'll go back to last semester for the course project. Okay. So course project page. That's a schematic of the star ADC. So you guys already derived the logic and remember the star logic, all the blocks in the circles, calculating all the numbers, intermediate values for the conversion. So that happens within this star logic block. This is a regular op-amp, and we have a lot of examples from the textbook we can directly use. So we're not designing an op-amp, right? Keep in mind. So it's going to be a given op-amp, and this is the sample and hold circuit, which I'm going to cover in the next following a few weeks. We have to start with charge pumps. It's very interesting because when I was looking at the ModWatt, the kit, growing bacteria to light up the LED, it also used the charge pump IC on it to boost the voltage from 0.37 to like 3 to 4 volts to light up the LED. Okay, so it's being used in many places. So that's the sample and hold circuit, and that's the star logic. I think we already did it in the past few weeks, actually in the very beginning of the semester. So we have to give a review on it on the circuit later on. So I put everything in this box. You're not able to see the schematic over here, but it's the sequencer and shifter do all the movings of the digits in the star conversion. And that's the R2R DAC. It's been in your quizzes and midterms for a few times, and you have lost a lot of points on that. So you must hate it. But you know, build a circuit is very simple. You just put it in the box. It's feeding a signal back, analog voltage back, because this is a DAC, so it's outputting an analog voltage, sending the output voltage to the comparator to generate all the bits, right? This is an array of D flip-flops. So whenever the data is ready, it triggers. It's like a door register. It triggers the clock and send the signal, the output, the final result to the output here. Okay. The reason I'm putting another DAC here is to convert the final result to analog voltage. For example, if I'm inputting a sine wave here, right, and the output over here is already a digital signal because this is ADC. I need a digital signal as an output, right? So the analog input with the digital output. But however, these 8 lines have all the values, including the intermediate values. Remember all the circles in the middle? So it has all the values in the middle. So I do need a door register whenever it's ready. Okay, I can sense it and trigger the D flip-flops and send the correct output over here. So this is just an array of D flip-flops, nothing else. And that output is a digital signal. If I want to verify it, most likely I'm going to visualize it, right? So I'm going to convert that digital signal into an analog point. If I'm having a sine wave, eventually I'm expecting a sine wave to be plotted as the output. So I do need a DAC to plot it, right? So eventually it looks like this. it's a super noisy, but it's an 8-bit ADC result. It's a sound wave. It's trying to follow that. If you have a low frequency for the clock, then you can finish the simulation in a few seconds, but the result is not as good as the one like this. So this one, compared to this one, it's the same circuit, but I just used a pretty fast clock instead of, you can see the clock, it's about 10 times slower than each step over here. So we'll go through the logic for the whole circuit later on. But now you should know why we need a D flip-flop, because if you look at the schematic on the top, these are just registers, right? See, every single one here is a D flip-flop. And I do need a set and reset in it, right? So you can pick up the TI D flip-flop like the ones I used here. It worked really well. Like this one, right? Which is exactly the one on the paper here, okay? So we're going through all the gates, and so we understand what's going on inside. So this one has a set and reset, and this one is rising edge triggered. So we're not that patient, don't want to wait for a long time to receive the voltage. So whenever it samples, it triggers the output. So this is a rising edge triggered synchronous D flip-flop, right? Okay, I hope you guys can go through the circuit analysis like what I did in the last lecture. So I'm going to go through this really quick, and I'm going to give you guys some of the copies, the papers with the schematic on it, and let you go through it on your own instead of just myself keep talking here, right? So basically, I'm just repeating myself, but doing it slightly faster than last time. This one doesn't have a set and reset, but this is the basic structure of the TI's D flip-flop, right? So we are not verifying the set and reset functionality of it. So what we do is basically what? Just want to see if this guy is a rising edge trigger D flip-flop, right? Just want to verify if this guy is a D flip-flop. So where should we start with? Where do we guys start? Clock, yeah. So before the rising edge, the clock is giving what to the circuit? Before the rising edge, 0. So so 0 is gonna do what to the circuit? Right? Cool. First step, right? Keep in mind, first step, very first step every time. When clock is 0, you got 2 ones. So 2 ones is keeping this SR latch in the memory state, which is good because I don't want to change anything. When the clock is 0, it's not using the D flip-flop, it's not transmitting any signal to Q, right? I do want it to be a memory at that point. So what's next? So this is D, right? You want to start from D, right? Since you know this was 1, before the rising edge, this was 1, and you have a D bar here, D bar here, and D bar here, right? And because this is 1, you got a D, D. And because this is 0, so 0 and a D, and invert it, still 1, so stable. Here, you got a 1 here, because 1, 1, D naught, 0. So 0 and everything is still 0 and being inverted. You're getting 1, so it's very stable, okay? All right, so I think we are done with the initial state. Okay, no problem. So next, as a rising edge. So we are treating the rising edge as a really fast 1. So actually, at the rising edge, it becomes 1. So clock becomes 1. Okay. So this one from 0 to 1. Okay. What else is being changed over here? Because this is not 0 anymore, right? And this was D. Yeah, this becomes D naught, right? How about here? D, right? And this one it's going to update here to D naught as well, right? But since this is updating this line to D naught, but is it changing this result or not? It's not changing, which is great. So what about here? So this is changing to D, right? And still D naught, it's not changing. Right? And this will be changed to D naught as well, right? If this is changed to D naught, so you got a D naught and D naught, and it's still D. You're still getting a D here. So D and 1 and inverted is still D naught are stable here, right? Okay, so if you have D naught and D, are you getting a D here? How do you verify that? Yeah, if D is 1, we just give examples. We're assuming D is 1, then you're getting a 0 here, and this is 1, so you're setting it, right? So it's going to be a D later on, okay? So D being fed back to here, so we are getting a D naught, so D naught will be here and becomes D, so it's very stable. Right? If you want to make sure this is a DFF, so whenever the voltage is high, is logic 1, it shouldn't change anything, right? So we are assuming clock stays at 1, and now D will be changed to D naught. For example, D changes, right? D changes. It's going to happen to here. What? Is it affecting anything else over here? So this becomes 1 is still D. D is still D, right? And this is still 1, so D and 1 inverted is still D naught, so it's not changing. Okay, what about here at the bottom? So this is 1, 1, 1, D naught, still D, okay, unchanged, right? So it's a D flip-flop, the rising edge triggered. D flip-flop, and verify it, right? And for these ones, and we already did the standard reset last time. It's very simple, just to give it's a zero active, which means if you give a 0 to it, it should set Q, right? But at the same time, if you are setting the circuit, you cannot reset at the same time. So we give a 0, 1, or 1, 0. Okay, if you're resetting it, you give a 0 here, but you have to put a 1 here. You cannot just do 0 for both. Okay, but when you are using this circuit as a D flip-flop, you put a 1 to each signal line here. So you're not activating the set or reset functionality of it. Just use it as a normal D flip-flop. Okay, so now let's look into that. If it's just a normal D flip-flop, is it a rising edge? It's very similar to this one, right? I believe when we do the analysis, it should be very similar. We are verifying the D flip-flop functionality, so this must be 1 here, right? Must be 1s. Still, we start with the clock, a rising edge. When the signal is 0 here, you got 2 1s, no doubt on that. Because 0 is going to kill all the signal lines over here and give you a 1 to the NAND gate's output. Okay, so 1 will be passed to here. I got a D here, and this is the 1 because we are not resetting it. So we're getting a D bar here. Okay, so D bar here. It's the same signal line, so it's a D bar here, right? It's a 1, so it's a 1 here. Because clock is 0, so it's not changing anything, still 1. 0. And because the reset is 1, so this is also reset. We don't know what is this one for now, do we? This is 1, this is D bar, this is 1, so this is D. D. Okay? So we are able to find the voltage at every node, voltage node in the circuit when the clock is 0, right? What's going to happen at the rising edge? So rising edge, clock becomes 1. Let's see if anything is being changed right now. Are we considering D is also changing at the moment? Should we? When we are looking at the rising edge, should we consider the change of D or not? No, we are not. It's going to be too many variables, right? Because D, the reason we are looking at the rising edge is because we are assuming the rising edge is really fast. So D must be stable, even though sometimes, for example, D is changing like this, and you are sampling, so the rising edge is over here, right? It's still not at the edge of the D, so D is not changing. You are still sampling the DC voltage. You know what I mean? So a lot of times for the signal, there's a concept called setup time. Because the signal is very noisy, sometimes getting like this for really fast digital signal. When you zoom in, these are only like a few nanoseconds, so really fast. So do need some setup time. You need the signal to be ready, and then sample in the middle, right? Here's a clock. A rising edge, sample in the middle. You don't want to sample anywhere else. So for the ideal data, digital signals, it's easier, but for the real world signal, it just looks different than this one. You know, it's just super fast and have a rising edge and falling edge is comparable to the period or the on time or the full time. You need to sample exactly in the middle to get accurate data. Okay. So we are not considering D is changing at the moment of the rising edge, right? Because we know that we're sampling the signal in the very middle of the on time or full time of data, right? So when clock at the rising edge, it's changing from 0 to 1 for the clock, right? So what's going to be changed over here? D11 D bar, 11 D naught D. Okay, so this will be changed to D bar as well because the same signal line, right? And this will be changed to D, it's the same signal line, and same to this one will be changed to D bar, right? Okay, so this becomes 1 D bar, right? Which is D. So D comes back here, D11, still D naught, so stable. Same here, D naught, 1, D naught, D, stable. Do we need to update any other places? So we're good, right? So it's very similar to this one. It's just adding one more signal line on the top. But because that signal line, if you compare these two gates, the signal on the top is always 1 because we're not setting or resetting it. So it's not changing anything. Okay. So as long as we are having the same signal over here, it should do the same job. So if you have D bar and D, Q should be D, right? Okay. So if D changes to D bar, what's going to happen? During untimed clock, D changes to D bar. It's very similar to the last one, right? So D bar and the D will be 0. 0 inverted will be 1. This will be 1. So this becomes 1. Okay. And because it's the same signal line, so this becomes 1. 1, 1, D naught, still D. D comes back here. D11, D naught. D naught, 1, 1, D. It's not changing anything. Are we missing any signal lines? Anything else is not being updated? I think we're good, right? It's pretty much everything. So it's verified because rising edge is not changing D, and also rising edge is sampling D. But whenever it's at logic 1, when D changes, it's not changing Q. So this one, that's why it's called synchronous D flip-flop. So every time it samples here, it sends it to Q. There will be a little bit time delay, but it samples it and sends it to Q at the same time. It's not like I sample it and wait for a period of time and then a floating edge I send it to Q. It samples and send at the same time. And it's rising edge triggered. So it's very resistant to noises. If the signal changes, it's not going to affect the result over here. Okay. Next, we are going to run some simulations, starting with the very simple D flip-flops and move to the complicated ones. Let's see if I have, I think I have it here. let's do the SR latch first. That's what we did at the very beginning. So I'm using a NOR gate, a pair of NOR gates as an SR latch. So when you verify the logic of the SR latch, how do we want to design it? Because the combination of the inputs could be 1001, 1100, right? Let's just make it happen. So what I can do is I assign a pulse function and another pulse function, but adding a little delay here, or they have a different delay. For example, the first one, it's a on voltage, off voltage, time delay, rising edge, falling edge, on time, and period. So you guys should know the arguments in this function. So what is this one? Delay. Okay, cool. So I'm going to run it really quick. Ignore the spike. I don't know what is that. Plot pane. R S. Okay. Now let's see if we can verify the logic. So whenever R is 1, right? So we turn on R. We should have a 0 for Q. Is it happening? What's going on here? Does that make sense? Simulation results here. What's happening? What we are simulating right now, SR latch, right? So SR latch it's a NOR gate SR latch. So the memory state is 11 or 00 for the NOR gate. Is that 00? Yes. Okay. So when you have 0 here for R and 0 here for S, it's both zeros, it memorizes the previous state, so it's not changing for Q. Right? If you look at start from here, right? Start from here. Okay. I give R a 1. Okay, what's happening here? What is happening? Can anyone explain this really quick? On the TV, just point on the TV and let me know what's happening. Just describe it. Explain it here. Is the Q the inverse of Q naught? Not exactly, right? So what's happening? That's right. Yeah. Okay, so at the very beginning, I do have a 1 here, right? So 1 is going to give you what? No. That's a NOR gate. NOR gate SR latch. Okay. So 1 is not used, but we cannot control it here. It's just running all the pulse functions. So it's if you give a 1, it's giving you 00s, right? So you can see the bottom 2 signal lines. You got getting a 0 and 0 for Q and Q naught until here, right? Because our S is being put down to ground. That's why you are not having 1 anymore. But what you have over here, reset is 1 0. So reset. So Q is being reset, and Q naught is become 1 after that. So what is happening here? 0, 0 is a memory. So you had a 1, 0 for the output. So here 0, 0 is a memory. So memorize the previous state. So you look at Q here. It was 1, it was 0. And after that, falling edge of R, it maintains that 0 for Q1. And Q naught maintains that 1 after that, right? And now what's happening here is you flipped R and S, so it's setting the result. So Q is 1 and Q naught is 0 until here. Both R and S are 1s. It's not used, but it's going to work. It's just a voltage, right? So 1, 1 is going to give you a 0, 0 for both NAND gates, which is exactly what we have over here. So on and so forth, right? So this is how we verify the logic of SR latch. And for SR flip-flop, now it's a non-gate flip-flop. So when you put signals to the inputs, first you need a clock, and then the S and R logic. Just use two pulse functions and adding a different time delay. You can see in R, I have a 15 nanoseconds time delay. For S, I have 5 nanoseconds. So I can shift the signal to give you a different combination of the binary, 2-bit binary inputs to S and R. And now I can verify it by running the simulation. So S, R, clock, Q and Q naught. S, R, clock, Q and Q naught. I'm going to change the top Y limit to 6 so you can see the logic 1 over there. Okay. Is it working as we expected? So starting with S. So when clock 0, but looking at the third row first, right? So when clock 0, what's going to happen? If clock 0, clock 0, you're getting 1, 1 here, right? So 1, 1 is the memory. Now let's see, if clock becomes 0, if Q and Q naught memorizing the previous state. Here it does, it's not changing, right? No matter R and S, how they changes themselves. Here, look at here. Does it change? When clock becomes 0, Q changes. What's happening here? What is happening? So we probably have to look at the top. So what was the signal before the falling edge for the clock? You had a 1, 1 here, right? So basically, S, R, clock are all 1s. So we're having all 1s here. So we're having a 0, 0 here, and Q naught will be 1, 1. Right? They are 1, 1 during this time frame. Okay? Starting from here to here, you're getting a 1, 1 for Q and Q naught. Okay? So what's next? What's happening next? Clock becomes 0, but S and R are still 1. But why Q is not memorizing the previous result? What's happening here? So S and R are still ones, not changing, but clock had a floating edge to, it's actually keeping these two signals to be 1 and 1, right? It should memorize, but it didn't. Is that because of the dip over here? Hmm? There was a dip that triggers something, the feedback signal. But why it triggered it? So if you look at the similar place, it shows a different result, I think. Is it? Let's see. Floating edge. No, I'm not seeing a similar one. Just right here. I think the dip triggers something, if I'm right. So same to this part. What's happening here? Okay, so now let's look at this one. So starting from here, I have all ones for all the three inputs. If you look at the top three signal lines, 1, 1, 1, right? So 1, 1 is going to give you ones, right? So you do have ones here, okay? No doubt on that. Until here, what happened is R, so clock and R changes at the same time. So this is not going to happen in the real life. I mean, this is just a real bad example, but I think it's good to find out what's really happening, right? If you understand the circuit. So clock is having a floating edge at the same time with R, which is fine because clock if the zero of the clock will give you ones over here, but R is gonna change at the same time. So we really don't know what's really happening here, right? Because the clock is trying to disable the two NAND gates, but the R is changing at the same time. So you really don't know what's going to happen at the very beginning, because if R happens first, then it's going to change the state over here when clock was still high, right? And then if the clock goes to low, it's going to memorize that state. So let's take a look at the result here, see what happened. So after that, so did the R affect the result or not? Yeah, it does, right? Because you can see, oh, it tries, right? So there was a dip. There was a dip, but eventually it didn't. It was not successful, and right? Wait, it's if R becomes 0, S was 1, then actually it should set the circuit. So it's actually worked a little bit. But after that, during a really short period of time, when it arrives over here, what happened? Got a 0 zeros. It's a memory, so it's not changing anything. So actually the R, the floating edge of the R, really affect the result. Okay, so anyway, so this is just let's just take a look at the sequence. But a lot of times we have a way faster clock compared to the data changes. But in this example, you can see the clock is even slower than data, which is ridiculous. Okay. So that's a level triggered flip flop. And there's another one I drew on the paper last time in the last lecture. I think it's master slave D flip flop. But the thing is, we cannot set and reset it. You'll see this structure in a lot of places. Now let's run it and see. It's easier because it only has one input. Hmm. Okay. Spend a few seconds to take a look at it first. The good thing is Q and Q naught are really, so Q naught is exactly the inverted version of Q. And remember this structure? So when clock is high, the rising edge is being inverted, so the second stage has a falling edge. So it's actually blocking the signal from here to here. So when this guy is sampling, the first stage is sampling, the second stage is not functioning, so it's storing the data over here. Okay, but at the falling edge of the clock, whenever this line is falling, it's being inverted, so this line becomes rising. And it's going to send the data stored here, whatever stored here, to here. There's a rising edge triggered, actually. So now let's take a look at the graph, see if it's exactly rising edge triggered, right? So here's D, here's clock. So if you just look at this period, the rising edge samples a 0 from D, right? The rising edge samples a D. But falling edge send a 1 to Q. Does that make sense? Why does that happen? Is the first stage rising edge triggered or level triggered? First stage here. Take a second look at it. Is it so? It's very similar to the ISR flip flop. If we can have a rising edge trigger that simple, right? Why do we need this? So the ISR flip flop is what? It's a level trigger. So no matter what is changing at D, when clock is high, right? When clock is high, no matter how D changes, it's going to send the signal to the middle place here. That's storage for D temporarily. Does that make sense? So ISR flip flop is level triggered. How to control it? Make it edge triggered? There's no way to do it. So if you want to make it rising edge triggered flip flop, you need this, right? So the ISR flip flop is super simple. It's just a combination of logic gates. It's going to pass anything happens here to here. You don't have a switch. It's just a gate. It's the input of the gate. Whatever changes here is going to affect the result here. So the first stage is level trigger. That's why in the simulation in the simulation. Even though the rising edge here sampled a D to the middle pane here, right? However, the data changes during the clock's logic 1 time. See? If you look at the D on the top, after the rising edge, it changes from 0 to 1. So that change will be passed to the middle. Okay, so whenever the falling edge arrives, here's a clock, the falling edge arrives, the second stage's clock becomes the rising edge. It's going to trigger the transmission from here to here. So what's going to happen is whatever the D signal is at that moment, it's changing actually, it's changing. But whatever it is at the moment, at the falling edge of the clock, it's going to send it to the output. So that's why, here is the falling edge of the clock, see? The falling edge of the clock. To trigger the change, okay? It's going to send it a 1 to Q. So where is that one from? Where is that one from? Just right here. See, this little thing here. So whatever the one here, that one, the charge, I know the charge doesn't have a name, but if it has a name, then Charlie, okay? So the name of the charge here is called Charlie, right? So whatever the one here is also Charlie. Make sense? So this one over here, I know they're all ones, but if the one here is called Charlie, then here is Charlie as well. So the little one here is being sent to here at the falling edge. Because including the rising edge and on time of the clock, whatever changing here, like from here, right? Rising, going over here, this is being copied to where? Okay, so from the rising edge and the on time of the clock, so from here, so the data, right? So the data from here to here go up and go to the right a little bit. So that part of the signal is being copied to where? No, here. It's being copied to there during the clock time. But whenever at the falling edge of the clock, that moment, so that single data point, if you zoom in, right, that little data point is being sent to Q. There's a time delay. You can see if I zoom in, there's a time delay, but the falling edge here will send this data point to Q. There's a time delay, but it will be sent to Q and hold there, right? Why is holding the data there? Because so after the falling edge, right? After the falling edge of the clock, right? So data will be sent to Q, and it's holding Q there and not being changed. And why? Why? Why Q is not being changed? Let's come back here. So that's right. So let's see, okay. I have a falling edge and 0. Now let's pick up a thing like, for example, here, right? At the falling edge, it sends a 0 to Q, and still at the logic 0 for clock. But now D changes, right? So D has a rising edge and goes to 1 when the clock is 0. Is D being sent to Q or not? Here, D is changing, right? Is the change being copied to Q or not? No, Q is still 0, right? Why? Yeah, if the clock is low, right? If clock is low, it's sending a 1-1 here, so it's a memory. Okay, so whatever D changes, it's not going to affect the middle pin here. So the middle pin will be memorized or stored over there. So this is called a asynchronous D flip-flop, which is fine. I mean, it has its pros and cons compared to the synchronous D flip-flop, but the major issue of this structure, in a lot of places you will see this structure in the textbook, but it doesn't have a set and reset functionality with it. So for our ADC, you cannot use this structure. It's very difficult to add a set and reset. You can only set it or only reset it, but if you want to do both set and reset, it's just impossible. Okay? Make sense for simulation? How to analyze diagrams? It's been boring. Look at the simulation to verify the logic of the circuit of the D flip-flop. It's a very simple sequential circuit, but does that make sense? If you have a simulation result like this, are you able to analyze or verify the logic of the D flip-flop, like what I did over there? If you have a hard time to fall asleep, just analyze the waveform over here. Boring? Okay. Is it? Yeah. Yeah. That's right. And it's just the one flip-flop, right? If you look at the diagrams, it just has so many things in there. It could be more difficult, right? But you can see the circuit works. So we designed the sample and hold. It does hold it after the right sharp sample signal, and this analog input. So we are able to sample and hold it. It's a really interesting circuit to work with. No, not for now, but later. Yeah. See, it's a sample, it samples and track and hold. It works perfectly, you know. All right. We'll see you guys on Friday.